Outside, night temperatures sit well below zero for the third week in a row. In this part of the high country that winter, recorded lows in nearby settlements dropped into the negative 30s Fahrenheit and stayed there for days at a time. Freight stalled, cattle died in drifts. Inside most cabins, the weak point wasn't the stove or the roof. It was underfoot. Thin plank floors nailed straight to joists clicked, shifted, and opened hairline gaps that pumped cold air up from the crawl space every time someone crossed the room. The usual cure was more nails and more cursing. Yet in a handful of mountain cabins, builders used a different pattern. They snapped chalk to map every joist, then laced tarred twine and glue in a web under the boards. Floors stayed quieter and tighter, with almost no added lumber. This episode examines the method and the math behind those quiet steps. Fresh sawn 1-inch pine planks stacked outside a new log shell. Curls of sap-sticky shavings drifted across the hard-packed yard. Oxen still stood in the yoke, breathing hard after hauling the last load from a mill 15 miles downstream. The cabin walls rose plumb. The roof frame waited for shakes. The floor joists, hewn from local pine to roughly 2x8 equivalent dimensions, already rested on stone piers and sill logs at 16 to 24-inch intervals. Standard practice across the mountain territories followed a simple sequence: lay joists, nail planks, move in. The entire floor of a 12 by 16-foot room could be finished in a day if 2 men worked steadily and the lumber cooperated. No subfloor, no bridging between joists, no elaborate joinery. 3/4 to 1-inch thick boards, 6 to 8 inches wide, nailed directly to the upper edges of joists with cut nails every 12 to 16 inches. The assumption held firm: if the walls stood plumb and the roof shed water, a quick single-layer plank floor was good enough. Structurally, it worked. A man could walk across it. Furniture sat level. Stoves rested secure. The floor functioned as a platform, which was all most homesteaders believed they needed. Freight ledgers from Union Pacific depots and regional mills told the cost story. Sawn lumber ran $15 to $30 per 1,000 board feet at the mill, depending on species and grade. Wagon haul added another $1 per hundredweight per 50 miles. For a cash-strapped settler filing a claim under the Homestead Act, doubling the floor thickness meant doubling the lumber volume and the freight bill. That difference could represent weeks of wages or an entire season's small cash income. Tool requirements stayed minimal: an axe and broadaxe for hewing joists from standing timber, a crosscut saw for felling and bucking logs, a hand saw for trimming boards, an auger for drilling pilot holes, a claw hammer for driving and pulling nails. Most homesteaders already owned these tools or could borrow them from neighbors during a raising. No specialized equipment, no expensive hardware beyond the nails themselves. The National Park Service preservation briefs on historic log structures document this pattern across the Intermountain West. Foundations typically consisted of stone piers or sill logs set on shallow pads. Floor joists, identified as among the most vulnerable components to moisture and rot, bore directly on sills or sleepers. Flooring went down as board stock nailed perpendicular to joist runs. The system worked in the short term. The outcome, however, diverged from the assumption once the structure cycled through its first full year. Lumber dried. Planks shrank away from nail shanks. Seasonal moisture and temperature swings expanded and contracted the wood. Joists settled on their supports. Nails worked loose. Gaps opened between boards and at plank edges. What had been a tight, quiet floor in June became noisy and draft-prone by the following February. On paper, the section drawings looked sound. Under a boot heel, the floor told a different story once the first winter passed. Frost rime formed along interior baseboards where cold air seeped upward. Each step from stove to bunk produced a sharp tick, then a faint sigh in the dark. The sounds came from specific boards in predictable paths. Crossing to the door, walking to the water bucket, moving between the table and the sleeping platform. The same planks complained every time. The common assumption treated Squeaks as harmless settling. Old wood talking. The cabin finding its place. Experienced builders knew better. In wood-framed floors, squeaks usually meant parts were slipping against each other, not locking tighter. Sound came from friction, two components rubbing as load cycled. Board against joist, wood against fastener, metal against fiber. The physics operated at small scales, but repeated thousands of times. Green or wet lumber shrank as it dried, pulling away from nail shanks. A 3/4-inch pine board that fit snugly around a cut nail in June might leave a 1/16-inch gap around that same fastener by February. Inadequate panel spacing or joists set too far apart allowed deflection under load. A 200-pound step on a board spanning 20 inches between joists might produce only a fraction of an inch of flex, but enough to lift the plank off the joist surface and rub the nail hole against the shank. Repeat that movement 10,000 times over a winter, and the hole enlarged. The board moved more freely, the noise grew louder, joists themselves could shift. Those resting on marginal stone piers or partially decayed sill logs sometimes rolled slightly when loaded. Forest Service log building bulletins identify sill logs in contact with soft ground as frequent rot and settlement points. As foundations moved, the entire joist grid could distort minutely. Nails that had been driven perpendicular to grain now sat at slight angles, concentrating stress and encouraging withdrawal. The consequences extended beyond noise. Loosened nails began to rise, a phenomenon called nail pop. Boards shifted laterally. Hairline cracks opened at plank edges where tongue and groove joints had never been cut. These cracks made channels for cold air. Winter air pressure differentials, warm air rising inside the cabin, cold air pooling beneath the floor, drove convection through any available gap. Each squeak marked a place where the floor was literally coming apart, however slowly, and each gap represented lost heat. Over years, the cycles compounded. Repeated deflection widened nail holes. Wider holes allowed more movement. More movement accelerated wear on both fasteners and wood. Eventually, the floor required major intervention, renailing, board replacement, or complete relaying. Work that could have been avoided or postponed with better initial construction or early corrective measures. The sound most settlers ignored, as old wood talking was, in mechanical terms, their floor slowly disassembling itself. A chalk line reel sat on a shelf between kegs of nails and boxes of lamp chimneys. Beside it, a small sack of hide glue granules and several coils of hemp twine rested among ordinary carpenter's goods. None of these items cost more than a few dollars. None required special ordering. All sat within arm's reach on any given morning when a builder came to stock up before heading back to a claim. The assumption divided these items into separate trades. Chalk lines belonged to carpenters and track layers who needed to mark long straight lines on rough timber. Cordage belonged to freighters who lashed wagon loads and tied down tarps. Hide glue belonged to joiners and furniture makers who assembled chairs and cabinets with mortise and tenon joints. Each trade used its own materials for its own purposes. The outcome, though rarely recognized, was that all three materials could combine into a structural system beneath a cabin floor, without any new technology or imported goods. Chalk lines had served European and American carpentry for generations. 19th-century tool catalogs listed chalk boxes as standard kit. The device consisted of a cotton or flax line wound in a small wooden case charged with ground chalk, usually white, blue, or red, depending on the surface being marked. To use it, a carpenter hooked one end at a reference point, stretched the line taut across the work surface, lifted it slightly, and released. The chalk-coated string snapped against the timber and left a perfectly straight mark. On rough-hewn joists or raw plank floors, these marks remained visible for weeks. Hemp and flax cordage appeared in every frontier depot and general store. Tarred hemp provided weather resistance and better grip for outdoor lashings. Unbleached manila and sisal served lighter indoor uses. Diameters ranged from 1/8 inch twine for bundling to 1/2 inch line for heavy loads. Freight companies consumed miles of it annually. Rivercraft and ferries relied on it for rigging. The material was abundant, cheap, and universally understood. Hide glue had supported fine woodworking since ancient times. Animal-based adhesive made from collagen, it came as granules or sheets that required soaking and heating. 19th century woodworking texts specified a working temperature near 60 degrees Celsius. Mixed correctly, hide glue created bonds stronger than the surrounding wood in furniture joints, stair treads, and veneered panels. It remained workable for several minutes after application in cool air, then set firm as it cooled. Joints could be stressed within hours and reached full strength in a day. Log building manuals of the period focused heavily on chinking and daubing, the mud, moss, or lime-based compounds used to seal gaps between wall logs. These materials required constant maintenance as logs shrank and shifted. Floors, by contrast, received less engineered attention. They were considered finished surfaces, not structural assemblies requiring ongoing care. The supply shelf already held the cure for a talking floor. The catalog simply never listed those items on the same page. Wind-packed drifts covered fence posts to their tops. Carcasses of range cattle lay frozen along creek bottoms, throats and noses packed with snow where animals had suffocated, trying to breathe through the blizzard. The winter of 1886 to 1887, remembered across the northern plains as the Great Die-Up or the Hard Winter, exposed every marginal detail in frontier construction, from fence lines to floorboards. The assumption that had guided building decisions for years held that if a cabin survived earlier winters, it would survive the next one. Temperatures and snowfall might vary, but within ranges already experienced. The outcome shattered that assumption. This winter exceeded all previous records in sustained cold, repeated storms, and accumulated stress on structures and livestock alike. Climate data from weather stations and military posts documented the severity. Sustained sub-zero temperatures from November through February. Repeated blizzards that buried the landscape under crusted snow, too hard for cattle to paw through to reach grass. Northern Montana and Wyoming saw temperatures drop to 30 below zero and remain there for weeks. Snowfall totals exceeded anything in settler memory. Rivers froze solid. Freight stopped moving. Rail lines disappeared under 20-foot drifts. The human toll appeared in agricultural reports and territorial surveys. Hundreds of thousands of cattle died across the northern plains. Some ranchers lost 90% of their herds. The open-range cattle industry, which had dominated the region's economy for over a decade, collapsed almost overnight. Ranches went bankrupt. Investment capital fled. The era of driving cattle north from Texas to fatten on free grass ended. Cabin-level consequences mirrored the larger disaster. Frost worked under foundations, heaving stone piers, and lifting sill logs, repeated freeze-thaw cycles at the margins of the season, and sustained deep cold at its peak, expanded and contracted every timber in the structure. Joists flexed, boards shrank, nails loosened. Gaps that had been hairline cracks in milder winters opened into visible seams. Fuel consumption spiked. Homesteaders and small ranchers burned wood and coal at rates that strained their stockpiles. Agricultural reports from coal districts noted the difficulty of keeping buildings warm where construction leaked air. Families that had built quickly and cheaply found themselves spending more time cutting firewood, more money on fuel, and more effort sealing gaps than they had anticipated when they chose fast construction over careful work. When a winter strong enough to end the open range hit these basins, even the smallest construction shortcuts started charging interest. A settler chipped failing daubing from a wall joint and packed in fresh mix while snow still sat in the yard. Maintenance on log structures never stopped. Walls required annual attention. Roofs needed periodic replacement. Chinking between logs had to be inspected and repaired each season as timber shrank and compound cracked. The assumption prioritized walls and roofs. These were the primary weather barriers. If walls stayed tight and roofs shed water, the structure was sound. Floors ranked as secondary concerns, walking surfaces, not critical components. The outcome showed that documented log building improvements helped overall performance, but often left floors as the persistent weak link. Better foundations became standard practice after early failures. Stone footings raised sills above ground moisture. Drainage channels directed water away from piers. Keeping lower logs dry extended their service life and reduced settlement that distorted the frame. Forest Service bulletins on log preservation emphasized these measures as essential first steps. Corner notching evolved toward tighter joints. Simple saddle notches gave way to V-notches and dovetails that locked more securely and shed water better. Each style reduced air infiltration and improved structural stability. Builders learned to orient notches to drain rather than trap moisture. Chinking and daubing systems grew more sophisticated. The best practice layered materials, wood strips or flat stones as backing, then clay or lime-rich daub pressed firmly into gaps. Some builders added fiber, horsehair, dried grass, or oakum to reinforce the compound and reduce cracking. Annual inspection became routine. Spring maintenance after winter's stress. Fall preparation before the cold returned. Floors, however, lagged behind. Adding a subfloor doubled lumber requirements and freight costs. Most cabins continued with single-layer plank floors because budgets and supply lines couldn't support heavier construction. The known fixes for squeaky floors offered only temporary relief. Renailing from above provided short-term quiet. Drive new nails beside old ones. The board stopped moving for a few weeks or months, but renailing enlarged existing holes and created new stress points. Over time, the problem worsened rather than improved. Sprinkling flour, talc, or graphite powder into gaps lubricated friction points and silenced squeaks briefly. The effect lasted only until the powder dispersed or absorbed moisture. It was a cosmetic fix, not a structural one. Wedging small blocks between joists and boards in localized spots reduced movement there but could create new stress concentrations at block edges. The floor transferred its complaints from one area to another. Modern guidance on floor squeaks distinguishes between stopgap measures and system solutions. Localized blocking and added fasteners treat symptoms. Gluing subfloors and ensuring proper spacing address root causes. Frontier builders lacked the vocabulary but understood the difference through experience. They would jack a wall and re-notch a corner, but few thought to engineer the one surface their boots tested 100 times a day. A small inspection hole cut in a floor corner revealed darkness and dust below. The homeowner lowered a lantern on a cord and peered into the crawl space. Joists ran perpendicular to the long axis of the room, their undersides rough from axe and adze work. Cobwebs hung between them. Dry soil lay undisturbed beneath. The space was cramped, perhaps 18 to 24 inches from earth to floorboards, but accessible for a determined person willing to work flat on their back. The assumption treated finished floors as mysteries. Once planks went down and furniture moved in, the joist pattern beneath became invisible. Repairs proceeded by guesswork. Nails went in wherever squeaks occurred, with no knowledge of whether the fastener would hit solid wood or miss the joist entirely. The outcome changed when a builder applied systematic thinking to the problem. With minimal tools, the hidden joist layout could be reconstructed from above and used as a design grid for targeted intervention. Step 1 required mapping the joists. Using a narrow auger bit or a stout awl, the builder probed between floorboards for solid resistance. A successful probe struck joist top. A miss found only air. Working across the room at regular intervals, the builder marked every joist contact point with chalk or pencil. Then he snapped chalk lines along the length of the room at each joist location, connecting the marks into continuous parallel lines. These blue or red traces revealed the skeleton that supported the floor. Typical cabin rooms measured 12 by 16 feet or 14 by 18 feet. Joists ran the short dimension, spanning 12 to 14 feet between sill logs. At 16 to 24-inch spacing, a room contained 5 to 7 joists. The chalk lines made them visible again. Step 2 mapped squeak corridors. The builder walked the UAS common paths, stove to bunk, door to table, hearth to washstand, and noted where sounds occurred. He marked these traffic lanes with secondary chalk lines perpendicular to the joists, then added small symbols or letters at intersections where squeaks concentrated. A simple grid emerged. Joists provided structural lines. Noise traces crossing them identified dynamic hotspots. The conceptual shift was subtle but profound. The floor stopped being an opaque complaint and became a readable drawing. Every intersection represented a specific board-to-joist connection. Every marked path showed where loads concentrated. Once the system was visible, any intervention, nails, glue, twine, blocking, could be placed where it would affect the most movement, not scattered at random in the hope of hitting something solid. The moment the joists appeared in chalk, the floor stopped being a mystery and became a map. A lantern sat on a flat stone beneath the cabin, throwing yellow light on joists, spiders, and packed earth. A man lay on loose boards positioned across the dirt, shoulders brushing the underside of the floor joists as he reached up with a small brush. The pot of hide glue sat on a heated brick wrapped in cloth to maintain working temperature. The smell, faintly sour, distinctly organic, filled the cramped space. The assumption held that working below a floor was impractical without full excavation or a proper cellar. Most cabins sat low to the ground. Crawling beneath them seemed more trouble than benefit. The outcome proved otherwise. Even an 18 to 24-inch crawl space allowed systematic reinforcement if the work was staged properly and targeted to high-need areas. Working conditions imposed limits. Light came from a single lantern or candle. Posture was awkward, lying flat or half-propped on one elbow. Glue cooled quickly in the confined space despite the heated brick. Each session lasted perhaps an hour before the worker needed to emerge, stretch, and reheat the adhesive. But the work was finite and progressed in visible increments. The pattern emerged from the chalk map above. Tarred hemp twine, 1/8 inch diameter, was anchored to a joist with a small nail or tied through a drilled hole. The worker then ran the line diagonally to the next joist, forming the first leg of a zigzag. Before securing it, he brushed hide glue along the upper edge of the joist and pressed the twine firmly into the wet adhesive. The glue oozed slightly around the cord, creating a mechanical bond as well as an adhesive one. He secured the twine at the second joist, then continued the zigzag to the third, fourth, and fifth supports. Each zigzag run followed a traffic lane identified on the chalk map. For a 12 by 16-foot room with 6 joist lines and 2 main traffic paths, perhaps 8 to 10 zigzag runs were laid. Then crosspieces, rungs, were added between adjacent zigzags, converting parallel lines into a ladder-like grid. Each rung spanned the distance between 2 zigzag runs and was glued at every intersection it crossed. The result resembled a fishing net or cargo web stretched horizontally beneath the floor. Material quantities remained modest, roughly 150 to 200 feet of cordage for the entire room. 1 or 2 small pots of hide glue, perhaps a pound of granules mixed with water to working consistency. Total material cost, a few dollars. Labor, 1 or 2 days of uncomfortable but straightforward work. The man in the crawl space was not adding lumber, he was adding connections. A few test boards lifted months later showed dark twine locked into hardened glue beads along the joist tops, like veins beneath skin. The adhesive had cured to a translucent amber. The hemp fibers, compressed into the glue while wet, now formed a continuous bond across the joist edge and up onto the underside of the floorboard. What had been two separate elements, plank and support, had become a composite assembly. The assumption stated that only more wood could stiffen a floor. Thicker boards, closer joist spacing, additional blocking between supports. Adding material meant adding strength. The outcome demonstrated that a properly arranged web changed how existing members shared load, acting like a diaphragm without additional thickness. Without lacing, each plank behaved mostly in isolation. A footstep's load passed through a small contact patch, perhaps 8 square inches where boot sole met board, down to a single joist through 2 or 3 nails. The board deflected between supports. The nails bore shear loads as the wood tried to slide past the fastener. Repeated loading concentrated wear at these point connections. With lacing, twine, and glue connected boards across several bays. The same footstep now engaged multiple planks through the tensile web. Load spread to 3 or 4 joists instead of 1. Each board contributed stiffness to its neighbors. The floor began to act as a unified panel rather than a collection of individual strips. Friction increased at board-to-joist interfaces. Hide glue added normal force, perpendicular pressure that enhanced grip between surfaces. Twine fibers embedded in the adhesive created additional friction paths. Movement that once concentrated around a single nail now distributed across multiple fibers, adhesive bonds, and fasteners. Slip decreased. So did the vibration and rubbing that produced squeaks. Vibration damping improved as well. The web absorbed and dispersed small oscillations rather than allowing them to build resonantly in a single board. A footfall that might have caused a plank to ring audibly now dissipated its energy across the connected system before sound could develop. Before and after comparisons remained qualitative in frontier practice. No instruments measured vibration frequency or deflection amplitude. But outcomes were clear. The number of audible squeaks per traverse of a main traffic lane dropped sharply. Nail heads that had previously risen under repeated stress now stayed flush. Gaps between boards remained stable rather than widening over time. Modern building codes now require glued subfloors precisely to prevent movement and noise. The principle was identical. Adhesive continuity distributes loads and prevents differential motion between components. The frontier method anticipated this understanding with available materials. The floor still moved under load, but now it moved together. A pail of water left near the door skimmed with ice overnight. Outside, the thermometer at the rail station recorded -28 Fahrenheit at dawn. This was the third extended cold spell since the Great Die-Up winter. The region's climate seemed locked in a pattern of extreme cold, punctuated by brief, inadequate thaws. 2 cabins stood within a mile of each other in the valley. Both had been built in 1883 using similar methods and materials. Both had survived the previous winter. But that spring, one owner had spent 2 days working beneath his floor, installing the chalk lace web. The other had renailed a few squeaky boards and called it sufficient. The assumption predicted that any floor system would revert to noise and gaps once enough freeze-thaw cycles worked on it. Wood moved with temperature and moisture. Nails loosened. Gaps reopened. No retrofit could resist the mechanical grinding of repeated seasonal stress. The outcome diverged along the line of that spring intervention. In the cabin with conventional repairs, fresh squeaks appeared at familiar locations. Boards that had been re-nailed the previous year worked loose again. Nail heads rose slightly above the surface, catching boot heels. Visible gaps opened at plank edges where boards had shrunk further during the sustained cold. Hoarfrost formed on the interior face of baseboards where cold air pumped up from the crawlspace through floor seams. In the laced cabin, minor new noises appeared near walls where the web didn't extend fully to the edges. But the central traffic lanes, the paths from door to stove, stove to bunk, hearth to table, remained largely quiet. Boards stayed flush to joists, nail lines remained stable. No new gaps opened in the main floor area. The small amount of hoarfrost that did appear concentrated at wall floor junctions, not across the room's center where foot traffic was heaviest. The difference wasn't absolute. Both cabins leaked some air. Both required firewood beyond what milder winters demanded. Both showed stress from the prolonged cold. But the cabin with the webbed floor maintained more of its initial performance. The distributed load system tolerated small differential movements, slight foundation shifts, minor joist rotation, modest board shrinkage, in a way that point-fastened floors could not. Ranch winter reports from the region documented ongoing livestock losses and structural strain. Fences pulled loose from frozen ground. Shed roofs collapsed under snow loads. Cottonwood trees split audibly in the coldest nights as sap froze and expanded. In a winter that pulled fences loose and snapped cottonwood limbs, the real difference inside two cabins lay under the rugs. Playing cards trembled on a saloon table every time someone crossed the room to the bar. A schoolteacher stuffed rags into floor cracks near the stove to stop drafts that lifted papers off children's desks. Ranch hands complained that bunkhouse floors bounced so badly under one man's steps that others couldn't sleep through shift changes. High-traffic floors in commercial and institutional buildings suffered problems worse than domestic cabins because loads were heavier, more frequent, and more concentrated. The assumption accepted noise and movement as inevitable in busy buildings. Only thicker planks, closer joists, or expensive hardwood flooring could reduce the problem. Improvements that exceeded most budgets. The outcome showed that informal spread of chalk mapping and lacing methods proved otherwise. Diffusion happened through the usual channels. Freighters waiting at depots swapped techniques. Ranch hands transferred between outfits and carried knowledge with them. Carpenters moved from job to job, adapting methods they'd seen elsewhere. A bunkhouse foreman who'd visited a homestead with a notably quiet floor asked how it was done. The method, string and glue under the boards, sounded implausible but cost little to try. One ranch applied it under a bunkhouse aisle. The improvement was immediate and obvious. Word spread. A saloon owner in a railroad town, tired of replacing bottles knocked off shelves by floor vibration, hired a carpenter to quiet the main traffic strip between the bar and the door. The carpenter used the chalk lace method under that section only, leaving the rest untreated as a control. Customers noticed. Other saloon owners inquired. Within 2 years, several commercial floors in the district had been retrofitted. Schoolhouses presented a different case. Limited budgets and seasonal construction windows made full floor replacement impractical. But school boards could afford a few dollars for twine and glue. Teachers marked the loudest zones, aisles between desk rows, paths to the stove, areas near the door. Carpenters laced those strips during summer break. Fall term opened with noticeably quieter classrooms. Variants emerged as the method adapted to different contexts. Some builders substituted thin stripwood for twine where scrap lumber was more abundant than cordage. The principle remained the same. Create a tensile grid beneath the floor. Others combined lacing with traditional mid-span blocking in especially bouncy bays, using the web to connect blocks to boards more effectively than nails alone. Building science would later document these same principles. Diagonal strapping and bridging between joists appeared in early 20th century guidance as standard. Upgrades for springy floors. The American Plywood Association eventually recommended glued subfloor systems specifically to prevent squeaks. The same outcome frontier builders achieved with different materials. Some carpenters mocked the idea of string under the floor until they walked across it. A preservation crew lifted a floorboard in a 30-year-old cabin. Beneath it, joists near the stone sill were dark and punky, carrying white fungal threads that crumbled when prodded. The wood had lost structural integrity. No amount of clever retrofitting could restore strength to members compromised by decades of moisture exposure and decay. The assumption, born from early successes, held that the chalk lace method could postpone any floor problem indefinitely. If it quieted squeaks and reduced movement in sound structures, perhaps it could rescue failing ones. The outcome established clear boundaries. Webbing could not restore rotten timber, correct grossly undersized framing, or compensate for fundamental design errors. Preservation reports from historic log structures identified sill logs and floor joists as the components most vulnerable to rot. They sat closest to ground moisture. They often received less careful material selection than wall logs. Poor drainage around foundations accelerated decay. By the time a floor showed visible sag or springiness, the supporting members were often compromised beyond simple repair. Overspanned joists presented another limit. A joist cut from marginal timber and asked to span 15 feet between supports would sag under normal loads regardless of how the floor above was treated. Lacing might quiet squeaks by preventing relative motion between boards, but it couldn't remove permanent deflection created by inadequate framing. Aging of the system itself imposed time limits. Hide glue became brittle after decades of temperature cycling and moisture exposure. Hemp twine decayed in damp environments, especially near drafty foundations where moisture condensed on cool surfaces. A web installed in 1887 might remain effective for 10 or 15 years, then gradually lose strength as materials degraded. Later owners, unaware that a web existed, might cut cords inadvertently during repairs or modifications. Misapplication created false security. An owner who installed chalk lace over questionable joists might assume the floor was fixed when in fact only the noise had been masked. The underlying structural problem continued to worsen, hidden by the temporary improvement. When failure eventually came, it was often more sudden and severe than it would have been with earlier intervention. National Park Service and Forest Service guidance on historic structure repair warned explicitly against expecting patch repairs to solve fundamental problems. Address rot at its source, replace failed members. Correct drainage and moisture issues. Only then consider improvements to secondary systems like floors. A quiet floor over rotten joists was not a success story. It was a countdown. A carpenter today runs construction adhesive along engineered I-joists before laying oriented strand board subfloor panels. The adhesive bead mirrors earlier glue lines along cabin joists. The purpose remains identical. Bond the floor into a unified diaphragm. Prevent differential movement, eliminate squeaks. The materials have changed. The principle has not. The assumption in modern construction holds that new materials in manufacturing, pressure-treated lumber, plywood, synthetic adhesives, precisely dimensioned components made squeak-free floors possible for the first time. The outcome reveals that the principle was already visible in frontier hacks like chalk lace, waiting for formal engineering to catch up. Building science evolved slowly through the 20th century. Early codes focused on load-bearing capacity and fire resistance. Performance issues like noise and vibration received less attention. But as standards tightened and residential expectations rose, the need for quiet floors drove research into why some assemblies worked better than others. The American Plywood Association and similar organizations conducted extensive testing on floor systems. They found that glued and nailed subfloors performed dramatically better than nailed-only assemblies in preventing squeaks and increasing stiffness. Adhesive created a mechanical bond that distributed loads across multiple fasteners and larger areas of wood. The floor acted as a stressed skin panel rather than a collection of individual boards. Modern codes now incorporate these findings as best practice. Subfloor adhesive is specified in residential construction standards. Installation instructions emphasize continuous beads along joist tops. The engineering vocabulary describes diaphragm action, shear transfer, and vibration damping, concepts that frontier builders approached intuitively with available materials. Preservation carpenters occasionally discovered evidence of the older methods when restoring historic structures. Opening a floor might reveal hemp cordage or thin wood strips glued beneath boards in patterns that suggested intentional reinforcement rather than random repair. Without documentation, the purpose remained unclear until someone connected the physical evidence to known performance problems and likely solutions. The frontier method anticipated modern practice by 7 decades. Chalk provided layout precision. Cordage supplied tensile continuity. Hide glue delivered bonding. The combination addressed the same mechanical issues that later codes would solve with engineered lumber and synthetic adhesives. Prevent components from moving independently. Distribute loads across multiple supports. Increase friction at interfaces. Reframing chalk lace as an early diaphragm and damping strategy shows that backcountry builders were making engineering decisions, not just roughing in shelter. What codes now describe in tables, one high country builder approached with a chalk line and a pot of glue. A ranch ledger from the period listed board feet of flooring, kegs of nails, and days of hired labor for repairs over 20 years. No line item ever read Squeaks, but several entries recorded relay floor, south room, or replace boards, bunkhouse. Each notation represented multiple days of work and tens of dollars in materials, significant expenses for operations running on narrow margins. The assumption treated noise and minor movement as issues too small to count in formal accounting. Floors were walking surfaces. If they held weight and didn't collapse, they functioned adequately. Cosmetic problems didn't warrant line items. The outcome, viewed over decades, told a different story. Reduced callbacks, fewer lifted boards, and lower fuel loss from drafts became meaningful savings in wood, money, and time. Consider the life cycle comparison. A full floor relay required stripping furniture, prying up old boards, inspecting and repairing joists, laying new planks, and reinstalling furnishings. For a 12 by 16 foot room, that meant roughly 192 square feet of flooring at 30 to 40 board feet per 100 square feet, 75 to 80 board feet total. At $2 to $3 per 100 board feet delivered, that represented $2 to $3 in materials alone, plus several days of skilled labor at $1 to $2 per day. Total cost for a single relay, $5 to $8 and a week of disruption. A chalk lace retrofit required 150 to 200 feet of cordage at a few cents per pound, perhaps $1 worth of hide glue, and 1 to 2 days of labor. Much of it the homeowner's own time. Material cost under $2. Labor, if hired, another $2 to $4. Total, $4 to $6, and the existing floor remained in place. If the retrofit extended floor life by even 5 years before major work became necessary, it deferred that larger expense and preserved the original investment. Over a typical cabin lifespan of 20 to 30 years, avoiding 1 or 2 full relays saved $10 to $15, enough to buy substantial quantities of other building materials or pay for winter fuel. Fuel savings from tighter floors added another dimension. Historical structure reports document that air infiltration through floor gaps contributed measurably to heating loads. Reducing drafts meant burning less wood per degree of interior warmth. Even a 10% reduction in winter fuel represented several cords of firewood saved, days of labor cutting, splitting, and hauling. The math remained informal in practice. Few homesteaders tracked these costs explicitly, but experienced builders understood intuitively that floors built or maintained to reduce movement paid returns over time. The quietness was pleasant. The durability was practical. The economic logic was sound. Treating squeaks as a diagnostic signal rather than a nuisance led to a method that improved comfort, reduced waste, and kept more heat in the room during the hardest winters of the open-range era. The principle scaled from single cabins to bunkhouses, schools, and commercial buildings wherever budgets were tight and floors saw heavy use. The chalk lace layout emerged from necessity, spread through informal networks, and quietly improved frontier life without fanfare or documentation. It left no patent, no manual, no formal record. The evidence survived in account books that didn't need repairs, in structures that lasted longer than expected, and in occasional physical traces discovered during later restoration work. In a country where one winter could end a cattle empire, the quietest floors belonged to people who treated their houses like machines, mapped, tuned, and held together by more than nails.